Okay, good morning everybody. We're ready to start. So the talk today will be given by Nikolay Kacharov. Nikolay has finished his PhD in February at the University of Heidelberg, where he was working on the formation and evolution of globular clusters through chemical abundances and kinematical analysis. And now he will shortly start a postdoc, always in Heidelberg, but at Max Planck Institute, where he will work on nuclear star clusters. And the talk that we'll present today is based on part of what he has been doing for his PhD thesis. So Nikolay has been visiting the IAC for 10 days already, and he will stay until the 19th of June. Okay.
Everyone. So indeed, what I'm going to present today is a project that I conducted as part of my PhD studies. It is a comprehensive study of this poorly known globular cluster NGC4372, and it is a project conducted in a collaboration with a lot of people whose name you can see down on the slide. I would like to start with some introduction, telling you what we know and what we don't know yet about globular clusters, how they formed and how they evolved. And then I will switch on to my own work, as I will present the chemical abundance analysis and the kinematic and morphological analysis of the globular cluster NGC4372. Then I will present a dynamical model, physically based dynamical model, which we obtained for this object. And in the end, I would like to conclude with some discussion on systemic rotation in globular clusters and the implications for the Milky Way halo. So as you see, the talk is a bit heterogeneous, so bear with me and ask questions if you have on during the presentation itself. So for a very long time, globular clusters were viewed as the perfect examples of simple stellar populations, meaning that they contain only stars which are born at the same time, bear the same chemical signature, born from the from the same initial mass function. Even in the beginning, it was thought that then you can judge the quality of your photometry by how thin, how narrow you can make the Carl magnitude diagram of a globular cluster. But then, in the 90s, when the Hubble telescope started operating with very precise photometry, we start seeing that globular cluster Carl magnitude diagrams are not that narrow actually. And here you see an example of the massive 2008 globular clusters, which present a clear separation in multiple main sequences. Already in the 70s, it also became clear that at least the red giant branch stars in globular clusters contain stars with different carbon and nitrogen abundances. In the beginning, this was regarded as an evolutionary effect, and people were thinking that this is just a dredged up material from the cores of these AGB stars that we observe today. Later, however, it became clear that such inhomogeneities are much more widespread, and they are present not only on the red giant branch, but among the main sequence, the horizontal branch, and basically in all populations within a cluster. From a spectroscopist's point of view, what we know about the average globular cluster today is that they basically contain stars with constant metallicity with very small spreads up to 0.05 dex. Most of the chemical elements are also constant, like the alpha elements, iron peak elements, and the neutron capture elements, with the possible exception of the S process elements, the slow neutron capture elements, for which I will be talking a bit later. Globular clusters also seem to bear the chemical signatures of the environment that they are known, and at least the elements that are constant within the globular clusters are usually the same as the majority of stars in the halo. However, we observed large spreads in the elements like carbon, nitrogen, oxygen, sodium, aluminium, and these are not only a minority fraction of stars, but a large majority of the globular cluster stars have these enhanced or depleted, respectively, abundances of these light elements which participate in hot hydrogen burning reactions. They also show large correlations among each other, like the famous sodium-oxygen anticorrelations or magnesium-aluminum anticorrelations. There are also stars with different helium abundances, and most likely the multiple main sequences here in these globular clusters are due to stars with different helium. This is not surprising, since the main outcome of the hot hydrogen burning, in which these elements like carbon, nitrogen, oxygen, aluminum participate as catalysts, the main outcome of these reactions is the production of helium. Here you see another example. This is a color magnitude diagram of the globular cluster M4, taken from the work of Marino from 2008. And you see here the sodium-oxygen anticorrelation. The stars covered with blue are those that have halo-like chemistry, enhanced oxygen abundance, and sour sodium. But there is a large fraction of stars that have enhanced sodium and depleted oxygen abundances. You can see that these stars are also separated on the red giant branch. The separation here is due to the different nitrogen abundance. Nitrogen is an electron donor, so it makes the opacity of the atmosphere. It increases the opacity of the atmosphere. So we basically see upper and cooler layer, and that's why we see these stars redder. The thing is that, however, that we don't really know how these multiple populations, how they formed. There are a couple of scenarios proposed during the last 10-15 years, but they all suffer from some caveats and still big unknowns. We know that we can produce these chemistry enhanced bottom capture elements in the course of massive stars or through hot bottom burning in massive AGB stars. But we don't know is how we actually can make such a numerous second population in a globular clusters from the ejecta of these stars. Some of the most famous scenarios go as follows. We start forming a primordial young massive cluster from a giant molecular cloud, and then in a timescale of about 6 mega years, the winds of fast rotating massive stars, or massive binary stars for that matter, accumulate in the center of the globular clusters, and from these ejecta a second generation of stars is formed. We need fast rotating massive stars, first because they are very efficiently mixed through rotation, and secondly they're rotating on the brink of disruption, so they can lose substantial amount of mass with relatively slow velocity. Similarly, for the massive binary stars, they form a common envelope which also loses a substantial amount of mass, which is enhanced chemically in the materials that we need to form the second population. This all should happen very quickly, because in a time scale of 10 mega years, the supernovae type 2, the core collapse supernovae, expel most of the gas and the star formation ends. The other famous scenario, so-called the AGB scenario, works on a slightly different time scale. According to it, in a time scale of 10 mega years, the cluster is free of gas, but then on a time scale of 100 mega years, the massive AGB stars start to evolve. Gas from their substantial winds, again, similarly accumulates in the center, from where we form the second population. The star formation from AGB stars can continue for a couple of hundred mega years until the bulk of supernovae 1A start to erupt and end any further star formation. From that point on, the cluster evolves for the next 10 gigayears and reach the state that we observe it today. The biggest caveat for these two scenarios is, however, that we need to form a very numerous second population from the ejecta of these massive stars, which are by no means the majority in the cluster. They're actually a very small fraction of the cluster mass. So from these ejecta, we can create only 1 to 10% of the mass that we need to form the second population in a globular cluster. Possible solution to this is people have proposed that probably globular cluster formed with a very different initial mass function. For example, they had a top-heavy IMF, which meant that there were much larger fraction of massive stars, or that the second population only forms in a bottom-heavy IMF, meaning that we form only low-mass stars, the stars that are currently living today and we see them now. There is no evidence, however, so far that there is a different initial mass function in globular clusters than in any other massive clusters forming today. Another proposition is that globular clusters were up to from 10 to 100 times more massive than we observe them today, and they managed to lose a large fraction of their stars, predominantly the first generation. Well, you can say that you lose mostly first generation stars because the second generation is formed in the center, it's more concentrated, so yeah, okay, you predominantly lose first generation stars. Also, the Milky Way halo is large enough that it can accommodate the mass, if it can accommodate the missing stars if globular clusters were 10 times more massive, or the 150 globular clusters in the Milky Way. However, we observe globular clusters in dwarf galaxies. The most famous example is the Fornax dwarf, which has 4 metal-poor globular clusters. We know that they all show the sodium-oxygen anticorrelation, so they have multiple populations, but the halo of the Fornax dwarf simply does not have enough metal-poor stars to account for such a large mass loss from its globular clusters. So we actually think that globular clusters couldn't have been much more than 5 times more massive than we see them today, and this is by far not enough to form to form a second population with such an enormous mass. Also, both of these scenarios require some dilution with pristine gas. So, for example, the AGB scenario, the bona fide AGB scenario, predicts a sodium-oxygen correlation instead of an anticorrelation, which we observe. And to correct for that, the authors of the scenario have proposed that somehow it mixes with pristine material. In the case of the fast-rotating massive stars, so massive binary scenarios, we don't have this problem. The chemistry there actually predicts the sodium-oxygen anticorrelation, but the ejecta of these stars are lithium-free, because lithium is destroyed in these hot stars. The second generation of stars that we see are not lithium-free. And also there are some evidence that the young massive clusters that we observe today, we don't really know if these young massive clusters will survive and turn into globular clusters, but they have similar mass. And we haven't seen any ongoing star formation in such clusters for more than 3 mega years of their formation. So recently, just in 2013, Nate Bastian proposed somewhat revolutionary scenario which doesn't imply the formation of multiple generations through multiple bursts of star formations. It assumes only a single burst of star formation. The idea is that on a time scale of 10-20 mega years, when the most massive stars start to evolve and eject material into the intercluster environment, there are still low mass stars on their Hayashi track, so they're still forming. They still have their accretion disks. So it is possible that while the ejecta of massive stars already evolving accumulate in the center of the clusters, passing low mass stars with their accretion disk accrete material and modify their chemistry. This scenario offers an elegant solution to the mass budget problem, since now we don't need to form an entirely new population. Actually, the stars need to accrete only about 50% of their mass to this swiping up with their accretion disks of material. And we only need to form not an entire initial mass function again, but just low mass stars, which we see surviving today in globular clusters. Here is a initial mass function of a globular cluster. This is the material that is supposed to be ejected and enriched in sodium, depleted in oxygen, having the required chemistry. And this is the mass of the stars that we need to form the mass of the stars that we observe today in globular clusters. The mass that needs to be accreted in the observed today mass of globular clusters, so it's more or less equal. The scenario also offers a nice solution to the lithium problem, because even if it uses as polluters the massive stars, the fast rotating massive stars and massive binaries, it only accretes part of the material, and even if this accreted material is lithium free, the star may have some primordial lithium when it was born. Well, this scenario also has its caveats. One thing is that simulations show that these stars don't remain fully convective for the necessary period of accretion to actually mix all the material. And second thing is that current simulations show that the accretion disk in globular clusters were destroyed much more easily than, for example, in the solar environment. So basically, these stars don't have their disks for a long enough period to accrete enough material. This basically revitalizes the mass budget problem. All right, we can add an entirely new dimension to globular cluster formation evolution by looking at their morphology and their kinematics instead of just chemistry. And what we see, well, initially globular clusters were thought as spherically symmetric and isotropic systems, well described to first order by kink profiles, for example, kink models. But with the improvement of observations nowadays, we see that they have quite extended profiles, meaning that probably there are halos of unbound stars. Some clusters have a significant degree of flattening. They show mass segregation, core collapse, or even tidal tails. From a kinematical point of view, we have cuspic velocity dispersion profiles, which are probably due to binary star interaction in the center, or even due to intermediate mass black holes, which could be the seat of supermassive black holes in the center of galaxies. Also, globular clusters have significant degree of differential rotation, some degree of velocity anisotropy. All these things have motivated the development of new dynamical models and the testing of new dynamical models, and these things also have implications on the formation of multiple populations. For example, if we take into account the HB scenario, it predicts that the second generation should form in a disk in the center of the globular cluster, so it will be predominantly rotationally supported. While, for example, in the accretion disk scenario, we expect that only stars which are on radial anisotropic orbits, these are actually the stars which go into the center to accrete material, would be the ones predominantly enriched in chemically changed abundances. So I was studying the globular cluster NGC4372. It is a typical representative of the old metal poor inner halo globular cluster populations with a metallicity of -2.3 It's fairly close objects located at 7.1 kiloparsecs from the sun. 7.1 kiloparsecs from the galactic center. I think it's it has similar distance to the Sun. It has been noted for luminous X-ray sources, which are typically found in the outer region. So people argued for inverted mass segregation in this object, or that it was recently gone through a core collapse and now it is currently expanding again. And its orbit is, well, it's a halo cluster. Its orbit carries it close to the disk, and it has survived multiple disk crossings. This is actually the cluster in question, and you see one of the reasons why it has been neglected so far is because it lies behind this strip of dust, interstellar dust cloud, and it suffers from a substantial differential reddening. So our goals for this study was to investigate its structural and kinematic properties, whether it's flattened, whether it is rotationally or pressure supported, to investigate its abundances and look for multiple populations, to give a dynamical interpretation of this globular cluster and put it on a solid physical ground, and to put it in the context of other globular clusters in the Milky Way and see what we can learn for the entire globular cluster system. We initially wanted to link the kinematic properties that we measure for these globular clusters with its multiple populations. Unfortunately, this didn't go quite well because, well, it's not the right object for that in the end, because it is too metal poor, and we managed to obtain good abundance measurements only for a handful brightest stars in our sample. But going to the observational sample, we observed with several pointings with the giraffe spectrograph at the VOT with high resolution, covering wavelength range between 6,000 and 7,000 angstroms. We observed about 250 stars, and you see here a histogram of the observed stars with blue compared with a model of the Besançon model of the galaxy for the velocities of stars in the foreground. You see that the globular cluster has a quite distinct velocity, although there is still some overlap with galactic stars, but through careful cuts in velocity space and in metallicity space, we are confident that we have obtained a clean sample of bona fide cluster member stars. And I want to start with the chemical abundances. First, when one goes for an abundance analysis, first thing is to obtain a proper atmospheric model for your star. To this aim, we use the automatic spectral synthesis called SME, or spectroscopy made easy, developed by Valenti and Piskunov. We used 5 free parameters to fit our spectra. These are the effective temperature, the metallicity, the microturbulence, macroturbulence, and rotational velocity of the stars. The first 3 parameters govern the strength of the lines, and the last 2 their shape. We used fixed surface gravities, assuming that we know the distance of the cluster, and using these canonical equations to calculate the log G. We interpolated from the grid of the alpha-enhanced Marx model from 2012 and used a line list from the Vault database, including hyperfine structure for some of the elements of interest, like scandium, barium, and europium. Here is a Hirschsprung-Russell diagram of our stars based on the physical quantities, effective temperature, and log G. You see that the method works quite well because all the stars that we the effective temperature and gravity for the stars that we obtain lie well on the theoretical isochron suitable for the cluster. And here is the point to make a note that actually some of our observations with VOT were not finished, and we have some suboptimal signal to noise to some of the data, which are pointed here with blue. These are also happen to be the fainter stars. So while we managed to get good velocities for all the stars in the sample, we didn't manage to get good abundances for all of them, so I decided to separate the abundance analysis for the two samples, for ones that have good signal to noise and for the ones that do not. You see that there are also some AGB stars here. But here are the metallicity that obtain, and there is a diagram of the iron to hydrogen ratio as a function of effective temperature. And you see that the red stars, which are the ones with good signal to noise, have very narrow distribution. We measure a mean abundance for the cluster of minus 2.25 dex with a very small standard deviation of 4.06. The case is similar with the suboptimal sample, although here you see that there is some trend with effective temperature, which we think is due to the lower signal to noise of these spectra and the inability of the code to completely remove the degeneracy between the parameters. If we take into, if you make a weighted mean taking into account the individual errors of each measurement, we end up with very similar estimate of the mean metallicity of the cluster and its intrinsic metallicity dispersion. Similar for the alpha and iron peak elements, we find very narrow abundance spread, so without any significant variations. You see here silicon, calcium, and titanium. The lower temperature stars are usually the brighter stars, so they have very high signal to noise. And you see that as we go to fainter stars and lower signal to noise, the dispersion starts to become more significant, but this is entirely due to errors, due to uncertainties of the measurement. Similar is the situation for the iron peak elements like scandium and nickel. Well, sodium and oxygen usually have very weak lines, and especially at the metallicity of minus 2.3, they are very difficult to measure. But at least for the about 15-20 stars for which we have very good signal to noise, we managed to derive good sodium and oxygen abundances. And you see the sodium-oxygen anticorrelation for this cluster, where here in this part are the stars that bear halo-like chemistry from the primordial population, and here are the stars with this globular cluster unique chemical signature. And here I want to say a few words about the S and the neutron capture process element abundances. And in particular, I compare the ratio of slow neutron capture process elements like barium and rapid neutron capture process elements like europium. Generally, one would expect that metal-poor globular clusters were born in an environment which was mostly enriched in R process elements, and this is indeed evident here since the barium-europium ratio is subsolar. When going to higher metallicity and AGB, so S process is predominantly made in AGB stars, which evolve on a later stage than the massive stars which give the R process elements. So usually more metal-rich systems are also rich in S-process elements because the clouds from which these systems form were also enriched in S-process on a later stage. What we see here in GC4372, however, and is interesting, is that we see some variation in the barium-europium ratio, and there are a few stars which have very low barium-europium ratio. These stars are enriched only in R process elements. The majority of the stars have some contribution of S process. In some globular clusters, people have found variation of the S process elements like barium, and have also linked this to the self-enrichment processes that also make sodium and oxygen, because S process elements could be made more or less in the same stars that make sodium, that enhance sodium and deplete oxygen. The thing is here we don't see any correlation between the sodium-oxygen ratio and the barium-europium ratio, so we rather think it is not the case. We rather see a correlation between the europium and the barium-europium ratio. So these stars are also quite enriched in europium. This is a bit difficult to understand, but it is not the first cluster that such a pattern has been observed, and it has been generally attributed to the to inhomogeneous mixing of the primordial cloud from which the cluster formed. So this result is based on the giraffe spectra analyzed, but there was recently published a paper by a different team based on the UVIS observations of the same cluster, and they also confirm the same behavior of the neutron capture elements. And yeah, also here, this is the europium line that we measure. It is also quite weak, and these are the spectra of two stars with very similar chemical, similar atmospheric parameters, and you see here the difference in the strength of the europium line. Okay, so I'm moving to the next part of the talk, which is about the kinematic and morphological study of this cluster. So here I have basically plotted the velocities of all the stars we have measured as a function of the radial distance from the cluster, and by binning them and by looking at the dispersion at different bins, we end up with a velocity with a velocity dispersion profile looking like this. Here it is fit with a Plummer profile, and by no means I want to say that the Plummer profile is a good representation of this cluster, but it gives some estimate of the central velocity dispersion of the cluster. We have calculated the dispersions using a maximum likelihood approach, which takes into account the individual uncertainties of each velocity measurement. So we actually look into into intrinsic dispersion rather than dispersion inflated by errors. Well, we have initial estimate of the central velocity dispersion of about 4.5 kilometers per second, which would give a dynamical mass of about 1.7, 10 to the 5 solar masses, typical for the lower mass end of Milky Way globular cluster populations, and the mass to light ratio of 1.5, which is also which is not strange in any case. We also looked for rotation in this globular cluster. This is done by, for example, we take a line through the center of the globular cluster and we measure the difference of the mean velocity from the two sides of this line. We rotate it at different degrees and we end up with such a sinusoidal line. The extrema give us the position of the rotational axis, and the amplitude of the sinusoid gives us the mean, twice the mean rotational velocity. We can go one step further and try to obtain differential rotation profile for the globular cluster. This is done by once we have pinpoint the rotational axis, we go and measure the mean velocities at different bins along an axis perpendicular to the rotational axis. So we end up with this rotational profile. We find peak at the rotation of about 1.3 arc minutes, which is well within the half-wide radius, and then it starts to gradually drop. Something that I will focus later on is the rotation versus dispersion ratio, which we find in the order of 0.27, 0.3, which classifies NGC 4372 as a slow rotator, but it is still significant degree of rotation for its low metallicity and old age. Sorry, can you say? Yes, yes, that is true. That we actually, this is a lower estimate of the true rotational amplitude because we don't know the angle under which we see the cluster. But we did some simulations and tests, and we confirmed that the angle cannot be less than 45 degrees, and because otherwise we simply wouldn't see the rotational signal. And when it is between 45 and 90 degrees, it's basically it won't affect our modeling, which I will talk later. Yeah. Yeah. So yeah, so when we have established the rotational axis of the cluster and its degree of rotation, the next question is whether the cluster is rotationally flattened, or is it flattened at all. So we used archival photometry for the object from obtained with the WF wide field imager at the 2.2 meter telescope at ISO, and we decided to go for a Markov chain Monte Carlo method to simultaneously derive 6 parameters for the clusters. These are its centroid, ellipticity with position angle, half-white radius, and the foreground density. The method goes as follows. We give the probability of finding a star at the position x, y, yi, given the set of parameters p, with a Plummer distribution. It is chosen just for simplicity, and then the likelihood of the parameters is given as by maximizing the likelihood function, or for computational reasons we actually maximize the log likelihood function, which needs summation of the probabilities of the individual stars. What we obtain here is cluster with a half-white radius of about 3 arc minutes and ellipticity of almost 10% at a position error of 52 degrees. What you see here on the diagram is the bint profile of the cluster within elliptical bins of this ellipticity and position angle, and the line here is the best fitting Plummer profile. But it is not a fit to the bin profile here. It is the best fitting model on the 2-dimensional fit based on the maximum likelihood technique. If we compare the ellipticity of NGC 4372 with other globular clusters, so here we have the ellipticity versus rotation versus dispersion ratio, you see that it basically follows it follows the sequence defined by most globular clusters with such measurement. It is compared here with a model of isotropic rotator, self-gravitating isotropic rotator. Most clusters lie under this model, first because we have only a lower estimate of the rotation, but also because if we have anisotropy, well, anisotropy has some complex interplay between the ellipticity and the rotation versus dispersion ratios, which would also result into clusters which have higher ellipticity at lower rotational speeds. But of course there are some exceptions which lie up here, and astronomers haven't completely agreed on the sole reason, or maybe there is no sole reason of what causes ellipticity in globular clusters. Intrinsic rotation is one of the biggest factors. Anisotropy plays a significant role, but also maybe clusters situated in a tidal field also would be tidally flattened. Or it has been even proposed that clusters might stay in triaxial dark matter ellipsoids, so they follow the shape of this dark matter mini halo. And although the main paradigm is that there is no dark matter in globular clusters, we haven't properly measure that to a large extent, since they are very, very concentrated objects. We don't have good estimates of the velocity dispersion of these systems in a very large radii. All right, the last part is about the dynamical model. So we try to put the cluster on a solid physical base by obtaining self-consistent self-consistent phase space distribution function by solving the by finding a solution of the collisionless Boltzmann equation. We used a function of this form, which was specifically designed to allow for differential rotation, and it is a function solely of the energy and the integrals of motion. In this case, the energy of the full energy of the star and the z component of the angular momentum. According to the Jeans theorem, any function which is a function of only of the integrals of motion is a solution of the collisionless Boltzmann equation. So with this dynamical model, we managed to simultaneously predict, so to say, the photometry, the velocity dispersion, like the photometric profile, the velocity dispersion profile, and the rotational profile, which gives us a full dynamical understanding of the system, and it also makes predictions for its ellipticity and velocity anisotropy. Going to the bigger picture of the Milky Way globular cluster system, here I have plotted an H-metallicity relation of all globular clusters which also have good kinematic estimates. So the rotation for the majority of the globular clusters come from the study of Bellazzini et al. From 2012, and the ages are taken from the study of Marin Frank from 2007. Here is NGC4372, which you can see has slightly higher rotation for its agent metallicity. But yeah, there are other clusters like M15 also is staying here, and it also has very large degree of rotation. We see here two main trends of the rotation versus dispersion ratio. One is that more metal-rich clusters seem to rotate faster, and also younger clusters seem to rotate faster. There is also the famous dichotomy you can see clearly here of in the H-metallicity relation of globular clusters, and we believe that clusters that lie up here are bow in situ, and clusters that lie up here are probably accreted onto the Milky Way halo on a later stage. So these here, the fastest rotating globular clusters, are actually the ones associated with the disk and the bulge of the galaxy. So it is quite plausible that their rotation is, well, they have gained angular momentum due to tidal interactions with the galaxy. And up here we can, well, it's basically my understanding is that globular clusters tend to be born with higher degree of angular momentum, and they gradually lose it with age. We also found an interesting correlation between the degree of rotation versus dispersion ratio and this is here the half-white to Jacobian radius ratio. The Jacobian radius is the distance between the center of the cluster and the Lagrangian points. So it is an estimate of that how tidally filling a system is. And what it seems is that more tidally filling systems tend to rotate faster. And especially this is much better seen. I've divided the clusters based on their horizontal branch morphology. Clusters with very red horizontal branch morphology, generally the older systems that are slower rotators, and the ones with blue horizontal branch morphology, which are generally the younger systems, have clear correlation with the Jacobian radius. So this is another indication that rotation is induced by interaction with an external tidal field. Well, N-body simulations have shown that as the clusters expand and they start they develop tidal tails, and it is possible that we actually misunderstand what we call intrinsic rotation and globular clusters with actually observing a tidal disruption here. So yeah, this is still a work in progress, and it would be interesting to actually manage to distinguish whether we do see tidal disruption of globular clusters and we call it rotation, or it's indeed an intrinsic rotation. And this can happen by like observing rotation in the very central parts of the globular clusters and compare it to what we see in the outer parts. So with this, I would like to conclude. So yeah, I've presented to you state-of-the-art observations of yet neglected globular clusters. These were the first this is the first high-resolution study of this object. I hope I have convinced you that even a simple globular clusters, not by any means different from the bulk of the others, can actually be very complex objects. And we have carried a full and comprehensive dynamical analysis and full and comprehensive kinematic chemical analysis. We found evidence for inhomogeneous mixing for the environment from the cloud, in the cloud from which the cluster formed. And we basically argue that both chemistry and kinematics are important to basically distinguish or to understand how globular clusters formed and evolved, but still more observations, for instance, observations of clusters for which we have a lot of stars with good chemistry and kinematics are needed. Thank you.
Thank you so much, Nikolay, for this talk. And now we have some minutes for questions.
Thanks for this interesting talk. I have one comment and a question that I have not understood. The comment is when you were talking about the accretional scenario by Bastian, indeed the issues related to the evolutionary time scale of the priming sequence model, that is the paper by Franca D'Antona and collaborators, is really not an issue, because in that paper the evolution lifetime for priming sequence stars are completely wrong by a factor of 2, so this is not a problem. But there is a killing question, a killing issue concerning that accretion problem. One of the main feature of the multiple population phenomenon is the discreteness that you have in the photometry. The fact that you have in the scenario is almost impossible. Really, you have to perform extremely fine-tuning in order to obtain the discreteness. It's so impossible. Something that is interesting, but I have not understood, is you have shown the plot, interesting plot concerning the rotational velocity of the cluster and the Jacobi radius, something like this. No?
Yes.
And you find that it seems there is a clear correlation, a clear some kind of segregation between the blue horizontal, the globular cluster with the blue horizontal branch. So that you name it young, I think young concerning the kinematical properties. You are referring to the kinematics, I think. So what do you mean?
One of the things that governs the horizontal branch morphology is age. So generally, clusters with bluer or more extended horizontal branch morphologies tend to be younger than the ones with red.
No, because the blue horizontal, the horizontal branch morphology is mainly age is important, but also now we know that helium is maybe important, and many globular clusters that are extremely old, like 2808 or Omega Centauri, have a very blue horizontal branch, and now we know that the blue is mainly due to the helium enhancement associated with the multiple population. But this there is some explanation for this, in the sense. Why there is some kind of segregation between globular cluster with horizontal?
That's an interesting question that I actually, you are right that, for example, I think that the clusters with blue horizontal branch do tend to be younger, but I agree that it is not the only reason, and you have also old globular clusters with blue horizontal branch morphology. I'm not entirely sure why there is such a clear separation, at least in the rotational properties of these clusters. This has been it's also the correlation between rotation and horizontal branch morphology has been noted also already in Bellazzini. I think they also didn't have a very good explanation why this happens, and they were arguing yes, horizontal branch morphology is connected to metallicity, and more metal-poor clusters tend to rotate slower.
But
It's also connected to age.
But did you check if there is, for instance, a correlation also with the present mass of the globular cluster between the rotational properties and the total mass of the cluster?
Yes, I've checked, and there isn't
isn't.
a significant correlation. Yes. Oh,
Regarding
there tends to be also some. It's not as good as this one, but there tends to be a correlation, not with the horizontal branch morphology, but with how relaxed the system is. So less relaxed systems tend to rotate faster, but as I said, the correlation is less significant.
you are regarding the possibility that the IMF is playing a role there.
It has been noted as a possible explanation. I'm not defending it in any case.
Yeah, but in any case, it does refer to stars above, let's say, alpha solar, or the possible variations as stars above alpha solar, or just those below alpha solar. That's the
well, for example, in 8 Bastian scenarios, the accretion this scenario, the second population is only low mass stars are formed. So you have a very bottom heavy IMF. You basically miss all the massive stars. But in different scenarios, people have proposed either a top heavy IMF, so you have a large fraction of stars to a large fraction of massive stars to contribute material, but also that you basically form a second population only from only low mass stellar population.
But in any case, this top or bottom, whatever, varying IMF scenario should reflect on the abundance ratios you measure in the cluster.
Oh, there have been trials to measure the IMF within cluster. It is difficult because we have only the lowest mass stars surviving, like below 0.8 massive stars, 0.8 solar mass stars, and you have to go very deep into the main sequence. But what people see is that there is not a real variation in the IMF. It seems normal. But probably these studies are not concluded yet, and I think there is still discussion on the topic.
Just so looking at the, I might have misunderstood this, but looking at the kinematics results, the position angle of your rotation, or the axis of rotation, didn't seem to be coincident with the minor axis from the photometry, or
it is within the arrows. It is
which is, I guess you'd expect if there was rotational flattening
yes,
that they should be aligned. Right?
It is within the arrows. So
was it okay?
We find here position angle 136 degrees.
Yep.
And then this is 52 degrees, so they're roughly perpendicular.
Oh, okay. Okay.
So these are both plus minus 6-7 degrees. So
okay, so it's okay. Yeah.
So presumably you chose your wavelength range to measure europium and baryon at the same time.
We use the HR 13 and 14 grisms. So basically they cover the optimal number of different elements. So they cover a lot of alpha elements, a lot of iron lines, and a lot of...
but you don't get, for example, the resonance baryon line, which is bluer, at 4,500.
Yes, well,
did you get that one in?
No, we didn't,
you don't.
We didn't
Okay.
observe
So
that.
you only have the other line at 6,000 something.
Yes.
If I remember correctly, there were indications of the significant effects of non-LT in these lines, right? In metal poor stars.
In the NLT effects.
Non-LT effects, yes.
Yes. Well, in this case, actually, here I haven't corrected for the NLT effects. I checked them, and they're in the order of 0.1 Bex.
Okay. So they are not that large, even though you have a significant range in temperature. Okay, thanks.
Okay, so thank you so much again, Nikolay, for this talk.